Okay, welcome to CS867 QSC890. This is week 3, and we'll talk about communication complexity. The notes have also been posted on Piazza. All right, so communication complexity. So it's a very rich and well-studied, commonly studied setting in complexity theory. The basic setting is the following. Basically, well, we have two players, Alice and Bob. So let's draw them here. This is Alice, and we have Bob here. Okay, and there's also a function, a known function, f, and the function acts on basically two different strings. Okay, and it's a Boolean function, has Boolean outputs. And what happens is that Alice receives an input x, and Bob receives an input y. And what they want to do is they want to compute f of xy. Okay, they know f, and Alice knows x, Bob knows y. What they want to do is compute f of xy. This is a function that requires both of their inputs together in order to complete the computation. So what they'll do is that they'll transmit bits across. So Alice might send Bob some bit about her input, some bit 0, for example, and Bob can respond by sending another bit, and so on. So they exchange messages, and at the end of the day, they reach the output f of xy. So this is what they want to return. So they want to kind of output f of xy. Okay, so both Alice and Bob want to say this in the end. And of course, they want to minimize the amount of communication. So in this setting, any overhead computation that they have to do on their inputs on x and y is free. And we only charge for communicating. Okay, so in particular, they don't need to make queries to the strings x and y. They can just read all the strings x and y for free. But they need to communicate. So in particular, you can always solve a function f by using communication cost minimum of and an m, and that's because, whoops, what happened here? No, okay. Sorry. Okay. So they can always solve it using the min of n and m number of bits. Why? Because either Alice can send all of x to Bob, and Bob can then compute f of xy because he knows both x and y, or Bob can send all of y to Alice, and she can compute f of xy there. So it only requires minimum of n and m for every function. Whoops, for every function. However, for many functions, there's faster strategies in this. So we are kind of interested in Alice and Bob here. They want to minimize the amount of computation. They want to beat this trivial strategy of sending all of x to Bob or sending all of y to Alice. Okay, of course, if you send all of x to Bob, Bob computes f of xy. He can then tell Alice the answer. Here, Alice and Bob trust each other and they cooperate. So they're not adversarial. There's no risk here that Alice doesn't trust Bob or something. So if Alice sends x to Bob and Bob returns f of xy to Alice, that's only a single bit, then now they both know f of xy. This is only a +1 off from this minimum here. So okay, so minimum of n and m up to constant factors basically is the maximum possible communication complexity, but we care about improving the communication complexity for many functions. Okay, so this is the basic setting. So we kind of want to formalize this model to kind of formally define what it means to compute this function capital F. Okay, so to do that, we will basically rephrase the setting slightly. Okay, what we'll do is, we will have Alice and Bob again, and of course Alice gets X, and Bob over here, Bob gets Y. But now we will have a referee in the middle. Okay, we'll have this referee here. The referee, he has this hat. Yeah, excuse my drawings. So what happens here is that we can imagine that instead of Alice and Bob talking to each other, they talk to this referee, and he can obviously pass messages across. So he's an intermediary. Alice talks to referee can tell Bob what Alice said. And now we can imagine that instead of Alice and Bob wanting to compute f of xy, it's really the referee who wants to compute f of xy. Of course, he knows neither x nor y. So it's sort of a symmetric situation in respect to x and y. It's not like, earlier Alice knows one half, but not the other half. The referee knows neither half, so he needs to be told about both. So it's the referee is sort of standing in the middle and effectively just listening in on what Alice and Bob are telling each other, or we can imagine him in an active role. It's sort of equivalent. Everybody's cooperating here anyway, so it's all sort of equivalent in an active role where he is trying to figure out f of xy, and so he asks questions even to Alice and Bob and gets answers about those questions. Okay, so we can imagine him asking Alice something about her input, and Alice returns the bit of answer. And this is actually equivalent to Alice just sending a bit to Bob. So if Alice and Bob agree in advance on their strategy, then if we say that, Alice will send Bob the parity of her string, that's her first bit. She sends as a first bit she sends to Bob is the parity of her string. Well, that's sort of equivalent to the referee asking Alice, "Hey Alice, what is the parity of your string?" And then she returns the answer. Okay, and then the referee knows this instead of Bob knowing it. But of course, he can always tell Bob this if we want, but we can imagine the referee being the active player here. So, if Bob was going to do something with his input and with this information that Alice gave, suppose Bob, wanted to do something with parity of x and his input y. Well, whatever he was going to do, whatever message he was going to pass to Alice next, the referee can ask Bob this question. So suppose Bob was later going to take the parity of his string, take the parity of y, and XOR that with the bit he got from Alice. So that is some function of y, and that function depends on the bit Alice passed along. So the referee can ask Bob this question. The referee can ask Bob, the referee can tell Bob, "Hey Bob, what is the answer to the question of what would you get if you took the parity of your string and XORed it with this bit I got from Alice? What would you get?" And then Bob will return a bit of answer. Now the referee knows sort of the next bit that Bob would have said to Alice. So we can kind of imagine the referee being the only active player here. He asks Alice and Bob questions. He gets back 1-bit answers. And this will turn out to just to be exactly equivalent to Alice and Bob talking to each other. And we want the referee in the end to know f of xy. And again, if Alice and Bob talk to each other, then it's like asking for one of them to send the answer f of xy to the other. That way, kind of the referee can see it. So, it takes a little bit of thought, but it's not too hard to see that it's equivalent to say that there's a referee in the middle, and the referee asks Alice and Bob questions, and gets back 1-bit answers. And then the referee wants to compute f of xy. And the setting here is that the questions don't cost anything. The questions are free, and the answers cost 1 per bit. Okay, so the free will ask 1-bit questions at a cost of 1 per question, effectively, even if the questions are very long to send across. So we don't measure the complexity, the time it takes to send the question. We just measure the number of questions. So just in general here, the referee can ask, it kind of sounds like query complexity a little bit, with the referee kind of making queries to Alice and Bob. But there's a difference here, which is that the referee can ask any question about X and Y, about the strings X and Y. He can ask any question about Alice and Bob's input at all. So he doesn't have to just ask what is the ith bit of X. He doesn't have to pick an I and ask what is the ith bit of X. He can ask what is the parity of X. He can ask for any function of X, in fact. So the number of possible functions the possible questions he can ask Alice is the number of possible functions there are on n-bit strings. Okay, because and that's because basically, well, X here, recall, is in 0, 1 to the n. Okay, so we have here an n-bit string X. The number of possible functions on n bits. How many functions are there on n bits? Well, how many strings are there of n bits? Well, there's 2 to the n strings of n bits, right? So there's the kind of cardinality of 0, 1 to the n is 2 to the n. Okay. So the number of functions on this domain, the number of functions on 2 to the n different strings, Boolean functions, that is. Well, for each string, you can assign it either 0 or 1 in the function, right? The function is defined by its value in every string. So it turns out that there's 2 to the 2 to the n different functions on strings of length n. So the referee has 2 to the 2 to the n different questions he can ask Alice, and 2 to the 2 to the m different questions he can ask Bob. Okay, so we can just formalize this a little bit. We can say that, okay, so we can say, let phi x, oops, this is, let's just write that neater here. Let phi x, so let phi x be the string of all function evaluations on X. Okay, so phi x here is a string of length 2 to the n. And if you pick any function on n-bit strings, any function alpha, then at position alpha, at position indexed by alpha, then phi x will have alpha of x. Okay, so phi x sort of answers every possible question you can ask about x. It's a string of length 2 to the n. Okay, and we can similarly define phi y, and then effectively we can have the referee, because he can ask Alice any question about x, he basically can make queries to phi x, and he can ask Bob any question about y. So he's basically has the ability to make queries to phi y. So effectively, the referee is making queries to this phi x, phi y. Okay, so this concatenated string. This is a string concatenation between phi x and phi y. Okay, so we can think of that. So effectively, what happened is that we had f. Whoops, we had a string. Sorry, we wanted to compute f of xy. Okay, but what we'll do instead is we will have a query function that takes an input, the string phi x, phi y. Okay, and we will basically define this query function to be the same. So we'll define little f here such that little f of phi x, phi y is equal to f of xy. Okay, and little f here is going to be a promise problem. So it's going to be a partial function, and it's only going to be defined on input strings that look like phi x, phi y for some x and y. Okay, so in particular, how many such strings are there? Well, we know that there's 2 to the n. Whoops. We know that there's 2 to the n times 2 to the m pairs xy. Okay, and for each pair we get a string phi x phi y. So there's only 2 to the n plus m. There's only 2 to the n plus m different strings that little f is going to be taking as input. However, the length of the string, the length of the strings is 2 to the 2 to the n plus 2 to the 2 to the m. Okay, so usually we call n the length of the input. So let's call that capital N for a second. So let's set capital N to equal the sum to the 2 to the n plus 2 to the 2 to the m. Then this is roughly 2 to the 2 to the max of the 2. Right, it's roughly 2 to the 2 to the max. And here we have roughly, here we have roughly 2 to the max, or 2 to the 2 times max or something. Okay, so let's ignore that factor of 2 there. Okay, so what we get here is that the number of possible input strings is roughly log n, where n is the length of the input string. Okay, so if n is the length of the input string, we would normally expect the number of possible inputs to be 2 to the n, but instead the number of possible inputs is log n. So this is 2 to the n. So this is log n out of 2 to the n, or I should say it's roughly log n. It's roughly log n out of 2 to the n. Inputs to the little f. Okay. Okay. So we have here a very severe promise problem. We have little f here. This query function that models our communication function. This query function little f. It has a very severe promise. The promise that it's a very small promise set. We know that the input will come from only this log n different strings instead of out of 2 to the n possibilities for strings of length n. Okay. Moreover, what is going to be the query complexity of little f? Okay, so we know that the query complexity of little f, the deterministic query complexity of it, is going to be equal to the deterministic communication complexity of capital F. Okay, basically by the way we set it up, the query complexity of little f is how many questions the referee is going to have to ask Alice and Bob before he knows f of xy. So this is the query complexity of little f is going to be the communication complexity of capital F in the deterministic model, at least. Okay, so because of this, then the query complexity of little f is going to be at most the minimum of n and m. Okay, so we know that, let's see, that d of f is at most the min and m, because we know that there is a strategy, a communication strategy, where Alice just tells Bob her whole string, or Bob tells Alice his whole string. So in query complexity, that would correspond to the referee asking. I guess this is missing a +1 here, I think, but the referee will have to ask Alice what her string is, one bit at a time. So he asks, what is the first bit of your string? What is the second bit of your string? And so on. So he asks n questions to Alice. And then he asks Bob, hey, Bob, what is, f of xy where this is x? So, of course, we don't charge him from asking questions. So he can, in his question, tell Bob, all right, here's x. What is capital F of xy? And he can ask this question to Bob. And Bob will give a one-bit answer. So because of this, then the deterministic Fourier complexity of little f here is at most the minimum of n and m plus 1. Okay, so that's fine. How does that compare to capital N? Let's just assume little n equals little m here. Then this minimum here, we know that capital N is 2 to the n roughly, and here we have n. So this is this is at most basically this is at most log n. Okay, so this is the upper bound on the possible Fourier complexity of the function. So we know we have a very weird partial function here in Fourier complexity. We have little f. It takes in an n-bit string. There's a very severe promise. This promise is that there's only log n possible input strings out of 2 to the n. And moreover, we know the Fourier complexity is going to be at most log n. Okay, so it's going to be a very tiny Fourier complexity. But we care about if it's even smaller. So we care about the difference between log n and log n, or square root of log n versus log n. So we care about what is the exact Fourier complexity here of little f. I mean, I guess up to constant factors still, but we care about this difference between double log n and triple log n, or the difference between log n and square root of log n. And so, okay, so basically the conclusion here is that we can define communication complexity formally if we want a formal definition. One way to do so is to just define communication complexity to be Fourier complexity. To be this little f here, the Fourier complexity of little f. So we can say that one way to define the deterministic communication complexity of capital F, which we will denote by dCC, of capital F, we can define that to be the deterministic Fourier complexity of little f. Okay, where little f is, of course, a function that depends on capital F. So, with that as our definition, then, we do have kind of a formal definition of communication complexity like this, but, it's going to be a very weird query function. It's going to be a query function that's kind of very different from what we're used to seeing. Still, it's kind of convenient sometimes to realize that communication complexity, in a sense, is merely Fourier complexity, at least in the deterministic model. Okay, so that is how we define deterministic communication complexity, although it's often not how we think about it. So often the way we think about communication complexity is we think in terms of communication matrices. So we can view sort of the truth table of capital F. We can view capital F because it acts on X and Y. We can view it as, this matrix. So like if we view this grid here, the grid will be will contain bits, and we can think of the rows as being indexed by inputs X for Alice. So that X index is a row and Y index is a column. And this capital F basically determines and is uniquely determined by such a matrix where, that is filled with these bits that tell you what to output when you get some particular x and y. So a communication function is really just a Boolean matrix, okay? And a Boolean matrix is always a communication function. Another thing to note here is that because we can ask any question about x and y, and computation just on Alice's side on x or just on Bob's side on y, that computation is free. There's actually no particular reason to assume that x and y are n-bit strings rather than just objects from some set of size 2 to the n. I mean, the string structure doesn't particularly do anything anymore. So we often think of capital F as actually acting on this cross product, some set capital X times some set capital Y, and giving us Boolean values at the end. Okay, so we often think of capital F as acting like this. And here, capital X, you can think of it as 0, 1 to the n. And you can think of y as 0, 1 to the m for some n and m. And that the only difference here is that capital X and capital Y don't have to have cardinality that's a power of 2. So they're going to be finite sets, but you don't always have to have them have size as power of 2. But of course, any number is within a factor of 2 of being a power of 2. So this hardly matters. It's only going to matter up to constant factors anyway. So, just often we will denote a communication function like this, like f acting on some finite sets x and y, the cross product of some finite set x and y. But, that's equivalent to acting on pairs of strings. Here I have capital X, capital Y. So, always we will have the little x be a member of capital X, and we'll have little y be a member of capital Y, so that capital F of little x and little y is in the set 0, 1. Okay, so right, so then you just the communication functions f defined on x times y, it directly corresponds to being a matrix that with rows indexed by the set x and columns indexed by the set y. So this is called the communication matrix. Okay, and the way we often think of deterministic communication complexity is we think of it like this. We basically so we think of Alice knowing some x here and Bob knowing some y, and they want to find the bit of answer in the cell xy. Okay, and Alice will tell Bob something, and this one bit that she sends to Bob is going to tell Bob, eliminate some possibilities about x for Bob. So Bob will know that Alice's input is, some of the possibilities were eliminated. Like, for example, if Alice says, oh, the parity of x is 1, then Bob knows that Alice is not holding the all 0 string, for example, because this parity is 0. And many other strings, he suddenly knows Alice is not holding them. So if we think of kind of what they both know, if we kind of use this matrix to draw all the possibilities for x and y, then the first bit that Alice sends across sort of splits the matrix in two. It's as if you draw a line that splits the matrix in two, where, on this side, Alice sent Bob 0, and on this side, Alice sent Bob 1. Okay, and here, this is only after we rearrange the rows. So if we sort the rows, basically rearrange the rows, then we can imagine that Alice, we will put all the kind of rows of parity 0, we will put them on top, and all the rows of parity 1, we'll put them on the bottom. If Alice transmits a bit that represents the parity of her string, then she basically cut the matrix in two like this. And Bob will suddenly either know that either Bob will know that that Alice's input is a part of the top part of half of the matrix, or he knows that it's part of the bottom half of the matrix. And then Bob will further send Alice a bit, and his bit can depend on the previous bits. So that will correspond to effectively Bob splitting the matrix into two pieces. They don't have to be equal size here. And making a different split on the bottom half, because he can send a different type of bit, a different function of his input to Alice depending on what the first bit was. Okay, so let's just erase these labels here. So effectively, they keep going. So Alice can send a bit to Bob again, and this bit will split horizontally each of these boxes. Whoops. So, and so on, and Bob can keep splitting adaptively in each of the remaining rectangles. And at the end, when Alice and Bob know the output, then at the end, if they've determined the value of f of xy on all possible inputs x and y, it actually means that each of these rectangles became all 0 or all 1. Basically, each of these rectangles must have become monochromatic, because suppose there was both a 0 cell and a 1 cell in a single rectangle. So if a single rectangle contained both a 0 here and a 1 here, then when Alice and Bob are given x and y that lands within this rectangle, if they follow the protocol and kind of narrow down which rectangle they're in at the end, then at the end of the protocol, they still won't be able to tell the value of f of x, y if both 0 and 1 are in this rectangle. Because at the end of the protocol, all they will know, all that they'll both know is basically that they're somewhere within this rectangle. Additionally, Alice will basically know what the row is, and additionally, Bob will know what the column is. But that's all the information they'll have. Okay, so they don't both have knowledge of what f of xy is yet. Okay, when they both have knowledge of what f of xy is, that means that we've split the rectangles enough that each rectangle is either all 0 or 1. So here, imagine that every single rectangle is either all 0 or all 1. When that has happened, so that happening corresponds exactly to so that happening corresponds exactly to Alice and Bob both knowing f of xy. Okay, so or having written on the transcript, basically having transmitted the value of f of xy across. Okay, so basically telling the referee the value of f of xy. When they tell the referee the value of x of y, basically, then it means that they've reached this situation where in the protocol. So the protocol is a partition of this type, where they keep splitting the rectangles either horizontally or vertically, adaptively, and then they reach a situation where all the remaining rectangles are monochromatic. They're all either all 0 or all 1. Okay, and so this is often a better way to think of how a communication protocol works, a deterministic communication protocol works. Okay, and again, it's equivalent to the query definition. The query definition maybe is a bit nicer mathematically. I mean, it's a bit easier to formalize. But this kind of recursive cutting of the communication matrix until everything is either all 0 or all 1 is a more intuitive way to think about it in practice for analyzing the communication complexity of functions. So it's going to be important to know as well. Okay, so this is deterministic communication complexity, but of course, we really want to talk about randomized and quantum communication complexity. So, all right, fine. So already deterministic communication complexity was not too easy to define. It was already a bit of a mess. Luckily, we'll define randomized communication complexity to just be probability distributions over deterministic ones, just as we did in query complexity. Or in other words, we will define the randomized communication complexity, RCC, of f, we can define that to be r of little f, if we want. So let's do that. Okay, so this is going to be the randomized query complexity of little f. Okay, so this corresponds to the referee sending randomized questions to Alice and Bob. Okay, so this is kind of a natural definition. Of course, if we think of Alice and Bob communicating to each other via some randomized protocol, then what this corresponds to is basically it corresponds to them being able to share randomness. They basically here, we had the referee asking questions at random and telling Alice and Bob the questions. So if we imagine Alice and Bob only talking to each other, before they could have agreed on their entire questioning strategy in advance. The reason they don't need to send each other the questions earlier is that they could agree on the questions in advance in exactly which sequence of questions they'll send. They could have agreed on that in advance, and basically then they don't need the referee. But now with randomness, they would need to agree on the random bits in advance as well. So they would have to basically agree on the strategy and share randomness, basically have random bits available to them that are the same for both Alice and Bob. Okay, so that turns out to matter. So this definition of randomized communication complexity is actually called randomized communication complexity with shared randomness. Okay. There's another definition where they don't share randomness, where Alice and Bob only can privately pick random bits and send each other bits that depend on their private randomness. And again, they can agree on their strategy in advance before seeing the inputs. Okay, but once they see the inputs, they can't communicate anymore except by paying. And yet they can pick privately, they can pick random coins. Okay. As usual, we only make them succeed with error 1/3 or less, say. So, okay, so this is going to be a different model called private randomness model. It turns out it's a weaker model. So anything you can do with private randomness, you can also do with shared randomness. Why? Well, because it's not too hard to see. If Alice and Bob only have shared randomness and they now want to have private randomness, then they can take their shared randomness. Let's say they created a lot of random bits together. They jointly created random bits, so that they share these random bits. Alice can say, okay, my bits are the even ones, and Bob, your bits are the odd ones. Okay, so now Alice has random bits, and Bob is going to deliberately not look at them and ignore them. And Alice will ignore sort of the odd bit. Alice will ignore the Bob's random bits, which are the odd bits. So even though she could see them in theory, she's not going to look at them. And now basically Alice and Bob have private randomness, so they can simulate private randomness. If that makes them succeed better for some reason than shared randomness, then they can simulate this. Of course, they trust each other and they're cooperating. We don't care about them like cheating or anything like that. They jointly want to compute the function. And the point here is just that if they both know about each other's random bits, that's only ever better. It can never hurt them to know about each other's random bits in terms of computing f of xy. It can only help to know more things. Okay, so clearly shared randomness is a stronger model of randomness than private randomness. You could argue it's less realistic. So you could argue maybe we should care about private randomness. It turns out that private randomness can also simulate shared randomness to some extent with a loss of log n-ish, so log of little n. So if the inputs to Alice and Bob are n-bit strings, then by paying roughly log n communication cost, Alice and Bob can kind of send each other enough random bits to effectively simulate a shared random protocol. So this is kind of a cool fact about randomized communication complexity. And I've written out a proof in the notes, so you should check that out. I won't go through the proof in the video. It's not too complicated though. The idea is really just that well, Alice and Bob know that they can succeed if they had some shared random strings. Okay, and because they can succeed if they had shared random, if they had a shared random string, then some choices of this random string they would share lets them succeed, and others choices don't. So for any pair x and y they might receive, some strings of shared randomness cause them to reach the right answer at the end, and some strings do not. Okay, so Alice and Bob can effectively, pick a set of representative, randomness, representative choices of shared randomness, and they can decide on those in advance. And then with private randomness, once the protocol actually starts and they receive x and y, they can basically use private randoms to pick sort of one of these long seeds from the set that they picked in advance, describe it to the other party using only log n bits, and then simulate the shared randomness protocol with this new string they agreed on as the shared randomness. So it's a little tricky to see why you only need to transmit log n bits across to get the strategy to work, but it has to do with the fact that they can agree on only relatively few shared random seeds, basically, or shared random strings, and then that would already allow the protocol to work, basically. So okay, it's a little bit tricky to describe in video. I don't want to write out the whole proof on the board here, so I would just send you to the notes where a formal proof is written. Okay, so that means that if we don't care about this additive log of little n, then shared randomness and private randomness end up being equivalent. And therefore, we can basically define randomized communication complexity using randomized query complexity. So we can just appeal to the definition of randomized query complexity. Okay. Okay, and of course, since a partition of this type, like a recursively nested partition of the communication matrix, represents a deterministic algorithm, a randomized algorithm, communication protocol rather. So a deterministic communication protocol can be represented by this kind of recursively nested partitioning. So a randomized communication protocol can be represented by probability distribution over these partitions, recursively nested partitions like this. Okay, so this is one way to represent a randomized protocol. It's a probability distribution over such partitions of this type. Okay. All right. So this is randomized communication complexity. So that, as in query complexity, that's not too much of a definitional overhead on top of the deterministic case. But what about the quantum case? So quantum communication protocols. Should we define quantum communication complexity? Should we define it like this? Should we define QCC of capital F? Should it be defined as Q of little f? I mean, do we want to set this definition? Part of the issue here is that, so we kind of roughly argued that for deterministic protocols, anything Alice and Bob can do by sending each other bits, you can also do by having a referee ask Alice and Bob questions, and vice versa. So these models were sort of equivalent up to maybe this +1 thing. So we kind of argued that there, where we hand waved it roughly. And that was true for shared randomness model as well, for the shared randomness situation. But it doesn't turn out to be true quantumly, okay? So if Alice and Bob implement some kind of quantum strategy, it's not clear how the referee should simulate it. But maybe to highlight this problem, to really highlight what's going on, we can note that QCC of f, whoops, we can note that QCC of f is actually always 1, regardless of the communication function f. Okay, QCC of f is 1. Why is QCC of f 1? Recall that if you could query in superposition, a bit of parity queries. Basically, if you can send superposition to a long string that contains all the parities of subsets of a string x, then Bernstein-Vazirani lets you extract all of x with a single query. And so here, or maybe I should say QCC of f is O1. Maybe it's at most 2 or something, depending on exactly how we set things up. Maybe we should say that it's at most 2. Let's just argue that it's at most 2 here. So, okay, that's a 2. Okay, so the idea is that because this is assuming, sorry, I guess I got confused here a little bit. If we set QCC of f to equal q of the query function little f, then QCC of f will be at most 2. This is what I'm trying to say. So let me just, because I feel like I've been saying it wrong. So let me just say it again here. Okay. Basically, if we set QCC of f equals q of little f, then we would have this. Okay, which is bad because it doesn't actually seem true that Alice and Bob, by transmitting qubits or something, they don't actually have a way to compute all possible functions of their inputs using 2 qubits or something. There's no way to do that. So something here is wrong with the definition. So basically, in other words, I guess the claim that I'm making here is that the quantum query complexity of little f is most 2. Okay, for any little f that comes from some big capital F. Okay, why? Because remember that the queries we're allowed to make to little f are these long strings that contain all possible functions defined on x and all possible functions for y. And in particular, Bernstein-Vazirani allows us to extract the entire string x if we are allowed to make queries in superposition to subset parity queries on x. If we are allowed to ask, oh, what is the parity of this subset of x? And we're allowed to ask this in superposition over different subsets, then we can extract all of x in a single query. So here in this model, we are allowed to ask such questions. In fact, we're allowed to ask many more questions about x than just subset parity queries. So because of this, then we can extract all of x in a single query, and we can extract all of y in a single query. And then, of course, we can just compute f of y offline with no additional queries. So then q of little f is at most 2. So we really do not want to define QCC of capital F to be q of little f. This is a bad definition because it's at most 2, maybe even at most 1 for all functions capital F. Okay. So instead, we have to basically make a more complicated definition. We basically have to actually model Alice as getting an input x, and basically she will basically start with this superposition x and 0 in some A register, Alice register she controls, and Bob will start with y and a 0 on some Bob register that he controls. And there will be a message register C on a single qubit that they pass along. Okay, so basically what happens is that, let's name this register C. So what happens is basically at first, Alice applies some unitary to she applies some unitary U1 to these two registers. Let's say it starts with a 0 in C. Okay. And then she applies some unitary, okay, and she gets some kind of result like this. And then basically she passes C along. So C gets sent along. And then on Bob's side, we have this Bob. Bob receives C, and he applies some unitary U2. Okay. And then we can get, let's call this C1 here. So this will be C2, C2. And so, and we can call this like A1 or something. So then we can get, or sorry, this is still C1. The result will be some kind of B2, C2, let's say, something like this. And then C2 gets sent over here. So now we have A1, C2, to which U3 gets applied. Okay, and then we get, A3, C3. Okay, and then the C register gets moved here, and then we get B2 here, C3, and then we apply U4. Okay, and we get and so on. So we assume for simplicity that Alice and Bob will take turns speaking. They will take turns communicating, and they just modify this single qubit register C by applying unitaries to it. Okay, so Alice will apply a unitary to, we can assume it starts with 0, it doesn't matter, but you will apply a unitary on her side to get the C1, send the C1 register to Bob. It's 1 qubit, so that costs 1 to send across, and Bob will apply some unitary on his side and send it back. Okay, and so they make T such unitaries, and they've sent C back and forth T times. That has total cost T. And at the end, they want to output f of xy, so they want to measure some part of the register A and some part of the register B, some sub register of A and sub register of B, I guess, and they want to get f of xy there as a result for both. So they both want to output f of xy. So that's a quantum communication protocol. Okay, so this is how we define quantum communication protocol. And quantum communication complexity, so QCC of f, we will define as like min T such that there exists T communication quantum protocol. Okay, so and usually we allow error a third. Usually, of course, we can consider the settings where allow different amount of error or require exact quantum algorithms. So this would be QE in query complexity. So we can define QE in communication complexity analogously. Okay, so this is how we actually define quantum communication complexity. The previous definition with Q of little f, this definition here is bad. Because it would make quantum communication complexity trivial. Okay, but quantum communication complexity defined like this, how we define it below, is not trivial. It is not always at most 2. It's always at most min of n and m as usual, up to constant factors, up to, it's always at most O min of n and m, fine. That's the same bound as deterministic complexity, but we don't have any better bound than that in general, for general f, okay? So we can always ask for some specific f if we can improve that bound or not. So this is quantum communication complexity. And there's one other catch. There's a variety of variation on this, in which instead of starting with having Alice and Bob start with, just 0 here. Of course, Alice can apply any unitary on her side effectively for free. We're imagining kind of applying, well, it's going to be built into U1 really. So if Alice starts with any other quantum superposition register here, then by applying U1, it's basically equivalent to starting with the 0 register, depending on what U1 is, right? So that's not going to make a difference if we allow Alice to start with something else at the beginning. But what if we allow the initial state of Alice and Bob, this A and B, A0, B0, I suppose, what if we allow that to be entangled? So it's not a pure state that looks just a separable 0, 0 kind of thing, but it's entangled. Okay, so if we allow them to start with an entangled state, and here the intuition is, again, Alice and Bob got together to agree on the strategy in advance. They met and they agreed on the strategy, and then they got separated, and then they got their inputs. So if they met and agreed on the strategy, why not share entanglement? So they can meet, share entanglement, then get separated and receive their input after that. Okay. If they do that, we get something called the shared entanglement quantum communication complexity. And sometimes this is denoted by QCC star. Sometimes it's denoted just by QCC though. So the star is not always there. Or some people just denote it by Q star, and they don't reserve Q for query complexity. So they would call that Q star of F. So these notations you can also see in the literature sometimes, with a star denoting shared entanglement. For our purposes, though, we will just assume by default that QCC allows shared entanglement. So for us, we will allow shared entanglement. With shared entanglement. So the shared entanglement is going to roughly be a quantum analog of shared randomness. It's not going to be fundamentally different from shared randomness, intuitively at least. So we might expect that you can simulate shared entanglement without shared entanglement using only an additional log n communication. However, we don't know how to do that, so that remains an open problem, I think. As far as I know, that's still open. Whether there is such a result where we can remove the shared entanglement using O log n, or whether it's sometimes necessary. So we don't know the answer. We don't have any examples where shared entanglement actually helps, except by a log n factor. So we don't actually know if shared entanglement really helping. So that is an open problem. Does shared entanglement ever really help you? We'll assume that you have it, especially when we prove lower bounds. We will want to kind of assume that we want to eliminate quantum communication protocols even with shared entanglement. We want to say even those don't exist. So that would be a nicer thing to say than only to bound quantum communication without shared entanglement. Okay, so it's just a bit of a stronger result because shared entanglement gives you more power. So a lower bound is a stronger result against a lower bound against shared entanglement. Okay, great. So now we've defined quantum communication complexity. So we can also talk about one important concept in communication complexity is the rank of a communication matrix. So basically the observation is if a deterministic protocol, whoops. So a deterministic, what happened? No. If a deterministic protocol, splits the matrix into rectangles like this, and the rectangles are all monochromatic in the sense that they're all a single color. They're all either all zero, or all one. Okay, so this is a communication protocol, deterministic communication protocol, computing some function f. Then this is what it does. It can be represented as a partition like this, a recursively nested partition of this form. Then the observation is that this is if you didn't use too much communication, if you only did T nested splits, then you have at most so if you have this, if you could solve F with at most T communication, then we have at most 2 to the T rectangles here. We would have at most 2 to the t rectangles because you've every split splits each rectangle into 2. So each time we split, we multiply the number of rectangles by 2. So t splits means 2 to the t rectangles. Okay, so we have at most 2 to the t rectangles, and because they're all 0 or all 1 within each rectangle, then we can say that that f as a matrix, the communication matrix f, is equal to a sum of these rectangles, like it's a sum of this little all ones rectangle here, plus, with zeros around it, right? Plus this all ones rectangle there. So just take each of these all ones rectangles and just write f as a sum of matrices where you just have the all ones rectangle with zeros elsewhere. Okay, so then that is one representation of the communication matrix F, but that means that F is a sum of at most 2 to the t matrices of rank 1. And that's because each rectangle, an all one rectangle with zeros around it, is a matrix that has rank 1. Okay, there's only kind of one linearly independent row in such a matrix. There's every other row is either identical or it's all 0. So there's only the rank there is 1 for this matrix, which means that what does this mean? Effectively, this means that the rank of F, well, rank is like the rank of a sum of matrices is most of the sum of the ranks. So this rank of F is at most 2 to the t. Okay, where F here we use to denote its matrix, the matrix associated with with F. So in particular, log rank F. Log rank F is at most t, which we said was the deterministic communication complexity of F. Okay, so this is a really nice observation. It says that the logarithm of the rank of a matrix is at most the deterministic communication complexity. Okay, so it's really nice observation. In particular, let's use this observation for something. Whoops. Let's consider the matrix equality. Whoops. This is a function. So consider like F to be equality, equality on of size n. This is equality of on strings of length n. So what is the definition of this? Well, equality on x and y is equal to 1 if x equals y. Whoops. If x equals y, and 0 if x does not equal to y. Okay, and then this is equality on n bits if the inputs are n bit strings. Okay, so what is the communication matrix for equality? So here Alice and Bob get strings. We want to know if they got the same string or different strings. So what is the communication matrix here? Well, the communication matrix for this thing, first of all, the rows are indexed by x. So the rows, there's 2 to the n different values of x and 2 to the n different values of y. So here this is a 2 to the n by 2 to the n matrix. And when the row number equals the column number, we put a 1, otherwise we put a 0. So we really have 1s here on the diagonal. And we have 0s above and below the diagonal. So this is actually I, the identity matrix of dimension to the n. Okay, so equality n is just I to the n. That's the communication matrix of equality. Okay, now what is rank of the identity matrix? So what is rather the log rank? Well, log rank of equality. Well, this is exactly n, because the rank of the identity matrix is this dimension of the identity matrix, the size of the identity matrix, right? So it's to the n here. So log of the rank of I to the n is n. So log rank of equality is n. So we get that the deterministic communication complexity of equality n is at least n. We also know it's at most n or most on by the kind of trivial algorithm. So so it's equal to n. So that's kind of a very useful application of log rank. It's a nice observation that we can lower bound communication complexity using linear algebra, using rank. Okay, what is the randomized communication complexity of the equality function? With shared randomness. Well, the randomized communication complexity of equality turns out that it's O1. So it's very far from the deterministic case. So this is kind of neat. Why? Well, there's this interesting strategy where if Alice and Bob want to know if their strings is the same or equal, then Alice can basically, well, they have shared randomness, so they can pick a hash function, a random hash, basically, in advance, or sorry, using shared randomness rather. So they get their inputs x and y. They use their shared randomness to jointly pick some hash function, a random function, let's say. And then they apply that random function to x. Alice applies it to x, Bob applies it to y. And let's say Alice sends across the result. So that's a 1-bit result. And Bob compares the 1-bit result he got from Alice to the hash of his own string. And if they're the same, then they gain more confidence that the strings are the same. If it's different, they know for sure that their strings are different. Okay, so what Alice and Bob will do is they'll just repeat this a few times, let's say 10 times. Now, if x and y are different strings, then because we are picking this hash function at random, every time we have a 50% chance of discovering that the strings are different. So we say do this 10 times, then we will almost certainly discover that x and y are different. But of course, if x and y are the same, then all the hashes will be the same always. So to bounded error, since we're allowing bounded error, you only need to do this a couple times, even just 1 or 2 times for error 1/3, and Alice and Bob can have enough confidence about whether the strings are the same or different. So yeah, it's a kind of a really neat protocol. It uses shared randomness though. So you can ask, okay, that feels like you really fundamentally used shared randomness so that Alice and Bob can pick the hash function jointly and both know what it is. If you had to describe what the hash function is, well, that would be very expensive to have to communicate what the hash function was. So you can say, okay, isn't that cheating to use shared randomness here? But remember, as we showed in the notes, the private randomness version only can simulate any shared randomness protocol using only an additional log-n communication, additive log-n communication. So we get that sort of RCC with private randomness of equality. Whoops, what happened here? Of equality. We get that this is at most log-n. Okay, and the deterministic communication complexity was n. So we still get an exponential improvement. So what about Quantum, well, of course, the quantum communication complexity with shared entanglement can simulate randomized protocols with shared randomness. So that's O1, just because you can simulate the randomized protocol. Without shared entanglement, you can simulate randomized communication protocol with private randomness, and so you get at most O log n. Okay, so that's the weird situation of equality. And note that equality here is that, it's just a normal communication function. So it wasn't anything weird about it. So we get that randomized communication complexity can be exponentially smaller than deterministic communication complexity. And in a sense, this was even a total function. So we can even define partial functions in communication complexity if we wanted to. And partial functions would just be the same, the same situation, except, of course, a partial function. So we have f is x times y, 2, 0, 1 star to the n. Sorry. Yeah, to 0, 1 star. Yeah, so we can define a communication complexity to already be a partial function, to not give 0, 1 answers on everything in x and y. This will correspond to having a communication matrix that has some stars. So, so you can have a communication complexity like this. Like you can define a communication matrix that has 0, 1s, and stars, and Alice and Bob don't need to worry about succeeding on star inputs, right? And then this would be a partial function, and of course you can exponentially separate deterministic from randomized communication complexity for partial functions, like in query complexity. But in communication complexity, you can even exponentially separate deterministic and randomized protocols with total functions, with equality. Okay, so it's a kind of a interesting situation there. Okay. So another thing to note is that I have in the notes also a description of how composition works in communication complexity. So if we have a communication function f, if we have a communication function f, then and we have a query function, g, we can define the composition. So their composition is going to be a function. Well, it's composition g circle f, but sometimes it's written g circle f to the n, because we're going to compose g with n copies of f. And what that means is that it's going to be a new communication function. This is going to be its signature. And the communication function will work basically by saying, okay, so before, for one f, then of course we gave x to Alice and y to Bob. So for 1x we gave, so for 1f we gave x to Alice, y to Bob. Now we're going to do n copies of f. So we're going to give n copies of x, x1, x2, y1, y2, up to xn. Okay, so Alice is going to get n of them instead of a single input. And what they're going to want to do is they're going to want to compute, first they're going to want to compute f of x1, y1, and f of x2, y2, up to f of x and yn. This is going to be an n-bit string of outputs. And then they're going to want to compute g of this string. So G is a function that acts on n-bit strings. So they're going to want to compute G of the string. Okay. And so this has a Boolean value. Okay, so even though we have here n inputs to f, instead of outputting n bits, we output a single bit, which is this G applied to the n bit output of all the f's. Okay, that's the function, communication function, that is little g composed big F. So this is the communication function that you get from composing a query function with a communication matrix, with a communication function, I suppose. You get a new communication function. And so one cool thing about this composition is that it gives another relationship between query complexity and communication complexity. In fact, it kind of allows you to turn a query function into a communication function. So we already saw how to turn a communication function into a query function. Now we can also turn a query function into a communication function. Okay, so suppose you had a query function. So let's do this again. So new page. So suppose we had a query function, little f. Okay, this is just a normal query function. Okay, this is a query function. Suppose we have a query function, and what we want to do is turn it into a communication function with similar properties. So what we will do is we will pick some communication function G. Okay. Often G will be a pretty small one. So often X and Y here will be log n size. Will be strings of the set of strings of log n size, for example, or constant size. So they'll be smaller than n, than 0, 1 to the n. And then we will look at the function f compose G. Okay, this is a communication function. And it turns out that for various models, this, for example, so the deterministic communication complexity of this composed function is at most the query complexity of f times the communication complexity of G. Okay. And up to log factors, this is even true for randomized. So I'm using the squiggle there, the tilde, to hide log factors. And then I'm going to get this. And quantumly as well. Oops. Great. So this is the reason that these theorems hold is basically that if Alice and Bob want to compute F compose G, what they can do is basically first they can start with a protocol for F, either a randomized or a deterministic or a quantum protocol for F, whichever model they're in. So they start with a protocol for F, and they try to kind of jointly simulate it, proceed along with the protocol. They try to do what the protocol says to do. So the protocol says, oh, first query bit number 3. That's your first task. Query bit number 3. And now here for this composed function, query bit number 3, querying bit number 3 means evaluating G on X3 and Y3. That's what it means basically to query bit number 3. So Alice and Bob can then run the protocol for G in order to get bit number 3. Okay, and they run a randomized protocol if they're in a randomized model, or a deterministic protocol if they're in a deterministic model, or a quantum protocol if they're in a quantum model. Okay, and then they go back to the outer algorithm, and then they look for the next instance to query, and they proceed in this way until they're done. And so deterministically, this just works. So there's no real overhead to this. This strategy just computes F composed G. Randomized though, randomly, the issue is that when we kind of try to query the third bit, we compute G of X3 and Y3. G of X3 and Y3 gives us a randomized result, a noisy result. It has error. It's not perfectly certain in the output. So what we'll need to do is we're going to need to amplify it to reduce the error. And we'll reduce the error to something very small, like 1 over n or 1 over n squared. So small that we basically can argue that almost certainly we'll never encounter errors the whole protocol. And then we then, after amplifying all the G protocols, then we'll proceed as before. And this amplification costs O log n. But actually, it turns out that we only need to make it cost O log of R of F. So really, the log factors here it's not really a log n that's hidden. It's only a log of R of F. Okay, and similarly for quantum. So for quantum, of course, we make queries in superposition. So we're making these queries in superposition, or we're trying to. And what's going to happen is, let's say we will have one of Alice and Bob take charge. Let's say Alice takes charge, and Alice is trying to run the quantum query protocol. So Alice is trying to run the quantum protocol for F. But that's going to make queries in superposition to the bits of F. And she doesn't know the bits of F because that requires computing G. So then she kind of is going to send Bob, in superposition instructions. She's going to send Bob in superposition. Basically, now we're computing gadget number I in a superposition over I. So she's going to send this I to Bob, and then they're going to compute G. And so they're going to get like kind of I comma xi, basically, or I comma zi, I guess, where z is the output of G of xi yi. So that basically allowed them to make a query in superposition, so long as there's kind of a log n attachment to the communication for G that kind of indexes kind of it kind of tells Bob which gadget G's are currently computing, so that Bob is not confused. That also all needs to happen in superposition. So a little bit of thought is required to make sure this works. And it does work, but you do lose a log n factor, I believe, rather than a log q of f. Okay, but still kind of ignoring log n factors, then we do get the simulation to work, and we get that the quantum communication complexity of f composed G with or without, I think with or without shared entanglement, is at most, q of f times qcc of G plus log factors. Okay, so this gives us the upper bound. A natural question is whether the lower bound holds, whether this is tight, whether you ever have better protocols than this. And it turns out the answer is yes, sometimes you do, depending on G. So for example, the equality function we saw, what is equality really? Equality is asking, are all n of these bits the same? So it's kind of a big an and on n different questions. It's an and of n different questions, and the questions are, does a single bit equal a single bit, right? It's equality on one bit, and it's an and of size n composed with equality on one bit. This is equality on n bits. So we already know, so and on n bits, randomized algorithm requires n cost. It takes n queries to compute and on n bits. But we know that equality can be computed in O1 or log n, depending on your choice of public or private randomness. So somehow we kind of already know that this is going to fail. So when G is the equality on one bit and F is the and function on n bits, then then over here on the left side we're going to get like O1, whereas on the right side we're going to get On. Okay, so the upper bound of course always holds, but it's not tight for equality. And sort of the reason is that yes, it's not tight for all G. However, we kind of suspect that it's tight for rich enough G, for G that's complicated enough, that looks far away enough from equality, in a sense. So, there's some intuition here that it works for many G's, that this is tight, that this lower bound will hold for many G. And so what people try to find is they try to find a gadget G for which the lower bound holds, at least in terms of the R of F lower bound. So basically, you at least want something like RCC of F composed G, at least a dependence on R of F. Of course, even this is false for equality, but we kind of want to say, does there exist a G such that for all F this holds? So we kind of want to say, is there a gadget that's hard enough such that for any function that you compose with this gadget, the randomized communication complexity of this composed function is going to be at least the randomized square complexity of F. So that sort of makes this upper bound that we had tight, but only for some G, instead of like for all G. Okay. And so the answer is that this is sort of true, or more accurately, this exact statement is open. We believe it to be true, but if we allow the size of G to grow with the input size of F, if we allow G to basically be log n size, then we know it to be true. Okay, so basically this is known as a lifting theorem. So lifting theorems, and I've written about this in the notes, you can read it in the notes, but lifting theorems they basically, whoops, why is the line so long? Okay, they say that basically there exists a family of G's that have different input size. So it's Gn for n in n, for n in the natural numbers. Okay, such that for all F, for all F on n bits, let's just write it for deterministic communication complexity of F compose G log n is at least the deterministic query complexity of F. Okay, and let's lose some log factors. Okay, so what is this saying? This is saying, okay, if I want to turn my query function into a communication function, I can compose it with a sort of hard enough gadget that's not too large, a gadget of size log n, and I will get a communication function that I know I can solve using roughly D of F queries up to that log n. But there will be no better way of solving it either, okay, for deterministic algorithms. And we want this to also be true for randomized and for quantum. Okay, so the same thing for randomized and for quantum. So such a theorem is known for deterministic and randomized and not known for quantum. Okay, so this lifting theorems, it's believed to be true for quantum, but we can't prove it. This lifting theorem gives us a very clean way of turning any query function we want into a communication function simply by composing it with a gadget. And up to log factors, which are kind of lost all over the place, but up to log factors, the communication function will have the same communication complexity as the query function had in many models. So in deterministic, randomized, we conjecture quantum as well. And there is even other measures in query complexity, like degree and approximate degree and things like that. And they also lift to things like logrank and approximate logrank. So we kind of get a very nice correspondence between where we can turn any query function into an analogous communication function that has the corresponding properties. And of course, for at least deterministic and randomized models, we know that communication functions are query functions, just very weird query functions. So the conversion backwards, it doesn't work for quantum, but it works for deterministic and randomized in this weird log n sized setting, or it's kind of a very bizarre setting. But it allows us to turn a communication function back into a query function. And the rough intuition that I have in general is that the communication world is richer than the query world. You can design more types of functions. You can start by designing functions that come from query complexity, from lifted query functions, but you can design functions that are not lifted functions at all. There's kind of more richness, and a lot more things are open about communication complexity than query complexity, in part because it's a richer model. Okay, so I'll stop here, and we'll kind of go into more details as the class goes on into the different communication measures and some of the lifting theorems as well. All right.